Okay, welcome to this episode of SPCL VCast. I'm extremely happy that we could convince Keren. I mean, honestly, it didn't take much convincing. She fortunately agreed immediately to give us a wonderful update of her recent work on optics today. And we all know that Keren is a very well-versed person in this area, and I would give it to Martin to introduce her.
Thank you. So Keren Bergman is a professor of electrical engineering at Columbia University and also serves as a faculty director of the Columbia Nano Initiative. At Columbia, she leads the Lightwave Research Laboratory, which focuses on the intersection of computing and photonics. And she's also involved in the American Institute of Manufacturing Photonics Leadership Council, has received the IEEE Photonics Engineering Award, and is a fellow at Optica and IEEE. Keren will give us a presentation about petabit per second and sub-picojoule per bit communication using photonics. If you have questions throughout the talk, please put them and feel encouraged to put them on the chat. And at the end, we will have a Q&A session where Keren will answer your questions. Thank you, Keren, for being with us. And without further ado, the stage is all yours.
Thank you so much, Torsten and Marcin, for the invitation. I'm really excited to have this opportunity, and I'm very glad that we could do this online because it's very convenient. But I also love Zurich, and I have other colleagues at ETH, and hopefully look forward to seeing everyone in person as well soon. So I will be speaking. Let me just take out the people there. There we go. So as was mentioned, I'll be speaking about our work related to photonic, how to bring in photonics basically to these computing systems in a way that can deliver very high bandwidth densities while at the same time maintaining energy efficiency. So just as a bit of background, I think this is probably very familiar, especially to this group, is what's driving a lot of the communication needs, data movement needs in these systems, of course, is the explosion of AI application. And I'm amazed every time we plot this. This just, of course, shows, the size of a typical deep learning model and the number of parameters. And these models have been growing by just orders of magnitude. And this particular plot shows 6 orders of magnitude in just 6 years. So this is just, some other folks have indicated, maybe an order of magnitude every 18 months or something like that. But still, the growth is just beyond really any other technology entity that I've experienced. And we're up to 10 trillion parameters, maybe even actually more these days. So this is just explosive, and it does not seem to be abating in any way. So at the same time, we want to look at, especially from our perspective, at what may be some of the communication bottlenecks that handle this tremendous growth in AI models and deep learning applications. So if we look at the technology that, what I would like to say, sits within the socket. So you imagine an interposer, a board, so to speak, or we typically have some number of GPUs and high bandwidth memory that sits around that. And the growth in the GPU bandwidth, GPU to memory bandwidth within that board, within that socket, has been growing. To keep up with with the need for communication bandwidth, GPU to memory especially, to handle these AI applications. But the problem is that as soon as you get outside of the socket, so to speak, right, get out of the chip, the communication bandwidth is just has not been growing very much. So this is what I would call the internode bandwidth has been kind of a flat line if you plot it on this curve. And so that as we grow the systems, right, to handle, there is not the scale of the 10 trillion parameter models absolutely does not fit on a single socket. And so we have to scale the system to many, many nodes. And the communication bandwidth between those nodes is orders of magnitude, about 2 orders of magnitude less than what exists within the socket. So this is really a very, very serious bottleneck in communications. And so the scaling of the system is horizontal, right? So these are just some of the recent examples, with the Google Cloud and the NVIDIA systems. There are even newer systems right now. So, as within the board, within the socket, we have this, fairly scalable communication bandwidth. But as soon as we get out and try to really scale the problem, the communication capabilities just drop off a cliff. And one of the reasons for that is the energy consumption. So this actually shows the training energy consumption in as a function of the number of parameters, just to show that as we grow these models, size of these models, the energy consumption associated with the training is tremendous. So this doesn't really show the energy consumption broken down in terms of communication or computation, but just, it's making the point that, as we grow these systems, the energy consumption is a really key aspect as well. And is actually one of the reasons that we don't have this internode bandwidth, because the energy consumption associated with moving that data is too large with current technologies. I like to also show the same data really kind of in this slide, because it puts it in a different perspective. And this is from a paper that's a few years old now, but it just kind of shows this is not a large deep training model. You can look up the details in this reference, but it just kind of shows in terms of how much CO2 emissions, or in kilowatt hours, how much energy is being spent on the training itself, and compare it with the equivalent of the lifetime of a car, the carbon footprint of a car, air travel from across the US continent, for example, and how much carbon footprint we as a human take over 1 year. Of course, the US human year wastes a little bit more energy than the average global person. So this is a real issue, as we go forward. So let me kind of bring it back to the communication. And this is a plot that I'd like to spend just a minute on, because it combines a couple of different metrics that I think are really key to understanding, what photonics can potentially do in terms of alleviating the bandwidth problem, but also the communication and the energy consumption associated with that. So what you have here, and this is adapted from Dr. Keeler, who's a DARPA program manager in the US, what was known as the PIPES program that we are participating in. So on the y-axis here, we have a metric that combines the bandwidth density. So think about it in terms of how many gigabits per millimeter are coming out of the chip, right? The shoreline, what's known as the shoreline bandwidth density, and the energy consumption associated with moving those bits. So this is, the higher you are on the y-axis, the better both those things are. You have higher bandwidth density, and you have you have a better energy efficiency. So you are spending less energy moving that data. And on the x-axis is the distance that you're communicating. So if we look at these, so the red and the blue are basically electronic interconnects, and the yellow are the current commercially available optical interconnects. Okay, so let's just look at this, right here over very short distances. So this is really within the chip. This is going to SRAM or kind of local, very, very, very short interconnects. Electronics is actually quite good in terms of this combined metric. Very, very short electronic connectivity, within the chip, 3D integration, multiple layers, etc. We have on the order of kind of femtojoules, some number of femtojoules per bit for moving the data, and the bandwidth densities are also very good because we can have very high density electronics. But the problem, of course, is as you try to move the data over any distance, let's say to within the interposer, to the DRAM, to the high bandwidth memory, and then as you start to get off that socket, that metric goes way down, right? And I'll point out that this is on a log scale, and so it goes down by orders of magnitude. So the reason that we don't have the internode, the reason that you saw that yellow line be kind of flat while the GPU bandwidth and the memory bandwidth are continuing to grow is that, as soon as we get outside of that interposer or the socket, everything just kind of drops off the cliff. It just takes so much energy to move the data, and we just don't have the bandwidth densities that we need. So you might ask, here is optics, right? It says optical. So optics is really good at moving data over long distances, but the current technology that exists, like the pluggable optics, you might have seen that are used today in data centers and high performance computing systems, are not designed for high bandwidth density and energy efficiency. They're just not designed that way. They have like they're designed to maybe carry 400 gigabits or maybe in the future 800 gigabit, but they're not designed, they're bulky, and they're not designed for to be co-integrated with the socket. And so we are developing, and what I'm going to talk about today is really a new generation of photonic interconnects that are silicon photonic, basically co-integrated within the chip, not to move data on the chip itself, because electronics is actually quite good for that, but to really be able to take the bandwidth that exists within the socket and take it out of the chip with really, really good energy efficiency. The goal is to get sub-picojoule, maybe as good as 200 femtojoules per bit. That's maybe the record, and with very, very high bandwidth densities. Our target is to get to 5 terabit per millimeter squared. We can probably do even better than that, limited by I'll show you some of the technologies that can do that. Why is this important here is that once you are in the optical domain, this basically remains constant. So what I mean by that is once we have the data in the optical domain, it's distance, more or less, distance independent within the system. I can move that bandwidth, across the data center, within the rack, anywhere in the system, let's say within, a couple of 100 meters or so, without having to expend any more energy, and I can maintain that bandwidth density. So that's the main difference between electronics and photonic interconnects, is that really it's very simple. It's just that the optical transmission medium, the fiber or the optical waveguide, is low loss and very broadband. Whereas in electronics, it's very, as soon as you start to move high frequency interconnects, over any appreciable distance, the power that you need to, it's very lossy. So you need to re-up the power. it's just very difficult to do. The other advantage of optics is that basically very fundamental. We're using bosons, not fermions, so we can combine a lot of them together in the same pin. I can have a pin with as much as a terabit of data in it, because the different wavelength channels are not going to interfere with each other. Whereas in electronics, each channel or each signal has to be separated, or obviously I get crosstalk, and that's another issue that really limits sort of how much bandwidth, how closely you can put the pins, how fast you can drive those pins out of the chip, and that's really, we're kind of hitting that pain point on the electronic side, and that's why we're, there's a lot of effort now going to photonics. All right, so on the photonic side of the world, there's been a lot of progress over the last decade. It was mentioned in the introduction that I'm one of the founders of AIM Photonics. So this is in the US. It's basically an institute that was formed in 2015 that's completely dedicated to integrated silicon photonics. So it is a 300 millimeter state-of-the-art fab where we can design and fabricate photonics, on these SOI wafers. And this is just one example. Global Foundries has now a silicon photonic process, also 300 millimeter. Intel has silicon photonics. Of course, they're in Asia and in Europe and IMEC. So there are multiple. The ecosystem is now at the place where there are multiple fabrication facilities. So photonics is kind of in the the CMOS fabrication capabilities. It's not the same. Also TSMC is developing silicon photonic capabilities as well. So it's not all the way, of course, a CMOS, but it is there, and so there's the ability to have massive scalability manufacturing of these components now. I should also mention that with photonics, you don't need to be at the latest node. We don't need a 3 nanometer node or even a 16 nanometer node. This fab, for example, is a 62 nanometer fab because the optical wavelength is much larger. It's on the order of 1 or 1.5 microns. And so as long as you have the fabrication node, sufficiently good to create the optical waveguides and devices so that they're not scattering, not lossy, that's good enough. So we don't need to go to the fancy, expensive nodes that are used for electronics. All right, so how do we get these massive photonic links? What's the approach to this high bandwidth density? The approach that we are doing and some other groups are basically to use the wavelength domain, right? So in the optical domain, I can modulate or put data on different wavelength channels, and then combine all those wavelength channels in the same link. They do not interfere with each other. They're independent wavelength channels, and they can each carry data. So for example, I can have 64 channels of wavelengths, 64 wavelengths, and put 16 gigabit per channel on, modulated on those different wavelengths. And I will have in my link, I will have 1.024 terabit in that one link. And that's kind of our design. So what you see here, these little circles, basically what these are the silicon photonic devices that they take the laser light and they modulate that laser light at whatever frequency we choose. And then the circles on the other side, on the receiver side, are different. They're similar devices, but they have a different functionality. They basically filter out that particular channel. And then there's a detector, a photoreceiver that converts it back to the electronic domain. So again, on the TX side, there is an electronic signal that comes from the chip that modulates the signal with the data. And on the RX side, there is a filter that takes out the wavelength and then converts it back to the electronic domain. And there's a receiver on that. Now, obviously, a really important part is the laser. What do we do about the laser? How do we get all these different wavelengths combined? And so there are different approaches, right? If you could have just an array of laser chips, but that's very difficult to do. It's hard to get good yield on that, and there's also making sure that the wavelengths are exactly aligned to the channels where you want them modulated is also difficult to achieve. And so a really key technology that has been developed for this application is what's known as an optical comb generator. And so this is a technology that's been developed to create very precise frequency combs for metrology and other applications, but it's now being used in the interconnect world to generate many channels of light, many wavelengths of light with only one laser. So you have like one pump laser and then this very special comb cavity that generates these combs. And there's really good work by Kippenberg in Switzerland at ETH on these combs, for many applications. And here at Columbia, my colleagues Michal Lipson and Alex Gaeta are the combs that we are using here at Columbia as well. So that's just a kind of a very important component that's being developed. I'm not going to go too much into it, but it's an enabler of all of this technology. So we want to be able to. So here's kind of how we design these links, right? So you're trying to get the most bandwidth in the link, but with the least amount of energy. So it's a bandwidth energy co-optimization. So so we start with the comb and we have a certain number of channels in the comb. Let's say, like I said, 32 or 64 channels. And then we need to decide like how fast do we modulate each of the channels. We can go at 10 gigabit, 16 gigabit, 25 gigabit, 100 gigabit, all of those are possible. But the higher frequency that you go per channel, the more energy consuming that channel will be, because higher speed electronics means more power. So we have to choose the frequency of the channel, kind of co-optimize it, so that there's going to be kind of an optimal point where we get the best bandwidth and also the least energy. So like if we had 100 gigabit per channel, we would have a lot of bandwidth, but the energy would be very high. And if we had only 2 gigabit per channel, we would have very low energy, but then the bandwidth is not going to be very good. So so that's part of the design. The other part is, how many of these disks, in our case, do you put on a single bus? And that's just an optical design parameter, because we want to avoid, losses and things like that. So we have this kind of scalable architecture that allows us to scale beyond a single bus that you see in this picture. All right, so just kind of summarizing the approach to this technology, right? We want to, in order to really, dial down the energy consumption, we want to hit sub-picojoules, maybe even, in the hundreds of femtojoules regime. We want to maximize the parallelism that we have from the optical domain. And some of these combs can generate upwards of 100 or even 200 channels of light. And so that's really a really key enabler, because if we have a lot of optical channels, we can have less data speed per channel, and that really minimizes the energy. So it's about the parallelism on the wavelengths. also, if we are somewhat lower speed per channel, we don't have to do a lot of SerDes and signal processing, which minimizes the energy consumption. And then lastly, the other important aspect that we care about is thermal. Every optical device in the universe has sensitivity to temperature, because as you change the temperature, the index of refraction of whatever the material will change. And when you change the index of refraction of the material, it changes the characteristic of the device. So all optics is thermally sensitive in some way or another. And so we work very hard. There are different kind of tricks that we use in terms of making our devices by design robust to thermal variations by using different materials or by using larger, for example, in our case, we're using larger waveguides so that the optical mode is more in the center of the waveguide and doesn't see the fluctuations that are due to the sides of the waveguide. And I can go into more details of that if folks have questions, but that's a very, very important part of our research. We also do things like undercut on the wafer to, again, reduce the amount of energy required to thermally tune and control the devices. All right, so the next important question is, okay, how do you kind of put it all together? Assuming that you could make these optical chips. So one of the approaches is to use 2.5D integration. So this is an example of some work that we've done, where here's the optical transceiver, and I'll show more details of that. And here's the electronic chip, and they're both packaged on an interposer. And this is pretty good. This is a relatively straightforward way to package, and it's pretty good. But it doesn't really get us to the bandwidth density, because we have to take into account, if we look at the bandwidth density of this structure, right, where the electronics and the photonics are next to each other in this kind of 2D world, then we're going to be always limited in terms of the bandwidth density. If we could put the electronics on top of the photonics, right, in more like a 3D, that would yield a lot denser interconnect than the 2D, right? And the other issue with this 2D, which applies here, but also, there are some approaches where there's monolithic integration of photonics and electronics. So for example, Global Foundries has this process. There's like IR Labs, for example, is a company that uses that approach, where which is very good, because you don't have to have, it reduces the complexity of the packaging, where the photonics and the electronics are just monolithically integrated in the same process. But the issue is that it's 2D. And so you need to connect, somehow you need to have connections that go between the photonics and the electronics, whether it's monolithic or through an interposer. And that just limits, how much density, and also, there's also the length of this, the length of these connections. They have to be very, very close to each other. But if you go 3D, right, then it kind of opens up a lot more in terms of the bandwidth density. And that's sort of our approach. So here's like a little picture of the 3D, where you have the electronics on top of the photonics. And so you have direct connections from each of the electronic driver or in receiver circuitry, to the photonic device that's underneath that. And you can keep scaling that. And it's so this is this was one of our designs that was targeted 5 terabit per millimeter squared. You can kind of see this in this particular example, this particular work. The electronic chip is very simple. It was actually fabricated in TSMC, 28 nanometers, so not very advanced. And the photonics is fabricated in the AIM foundry that I mentioned earlier. And basically inside here is the link that I showed you. You can see over here. This particular design has 4 buses of 16 modulators. So it's this is the 1.024 terabit per link, and 4 buses of the receiver. And there are a couple of interleavers that because we have the to combine the different buses in that link. But basically, you can kind of see the layout here, and I'll show you a little bit more on some of our results. But the target here was for getting the 5 terabit per millimeter squared. So this was our first prototype. So here you can actually see the physical device. So you can see this is the PIC underneath, and the EIC, the electronic chip, is on the top. You can see here the fiber, the I/O, the optical I/O. Obviously, this is just a prototype. It's from a university, so it's not very fancy. And in this work, we had a lot of challenges because we have limited funding, right? So we have to design and fabricate the chips using multi-project wafer MPW runs, right? So we fabricated the photonic using an MPW run, and we fabricated EIC using an MPW run at TSMC. And then, so what we got back were dies, right? Just little pieces of silicon, and then we had to figure out how to package them in this 3D flip chip, package them in this 3D fashion with the grid of the grid of the pads and the contacts to achieve the bandwidth density that we wanted is a 25 micron pitch. So, which is not, it's not outrageous, but it's pretty aggressive. And so, aligning up on this 25 micron pitch, in the 3D integration was challenging. And we got this to work, and we published on it, but the yield here was not very good. We would only get only some of the channels, worked. And then we had, various packaging issues and shorts and things like that. So then we got, we were lucky enough or fortunate enough to get, additional funding in this project. And in our next fabrication run on the photonic side, we were able to actually have a custom wafer, just for us. So essentially, we own the entire reticle. And so in this custom fabricated wafer, we called it Cedar, that we designed. You can see here, this is a large reticle. It has many optical devices and structures that we were able to put on. But here on the top right is that PIC that's being used for the transceiver. So you can see here, very high density, 25 micron pitch, link design that's right here in this picture. But the key is that we had the entire reticle to ourselves. And so instead of having to package at the die level, we could send an entire wafer to be packaged. And so let me just go back here. When you're packaging something with a 300 millimeter wafer, instead of trying to align it up at the die level, it enables you to use tools that are much more advanced in terms of alignment and flip chip bonding and all of that. So that because of those 3D integration tools, we were able to get much better yield. In fact, 100% yield of the 3D package. So this was the first package that we got back with this wafer design. And when we saw these results, from the modulator buses, we were very excited. So this is here again is the EIC packaged, on top of the photonics. And so this was super exciting for us. to see the first sign, that there's connectivity between the electronics and photonics. And so here's more of that, and you can see here, the fully assembled. You can see the 25 micron pitch bumps. This is a full TX-RX, and the density here is actually even better than our design. It's 5.3 terabit per millimeter squared. So this is the highest, at least to our knowledge, bandwidth density ever that came out of a single chip. So we're very, very excited about that. In fact, we just gave a talk on it at a conference, Photonics conference, OFC, in March, just earlier this month. And so, we wanted to take a picture, for this paper, and the senior student who was working on this was, I think he was traveling or something, and so the more junior student, we asked him, can you go in the lab and take a picture, because we were trying to show a picture of our chip for a presentation. And so and we asked him, can you put something near it, like a coin? So this is a dime, to show it, just so people understand what the size is. And he put the dime right on top of our wire bonds, and we were very scared that the chip would be, that the wire bonds would break. But fortunately, everything is fine. And this is the chip, and it works. We actually have more than one chip. I'll show you. So this works very, very well. So this is, you see here the EIC and the fiber IO. So this was very exciting. And then we actually measured. And so in this particular design, each of the channels is running at 10 gigabit per second. The reason it's 10 gigabit and not 16 is actually is limited by the EIC. So the 28 nanometer EIC really could only drive the photonics up to about 12 gigabit or so. And so we decided to just run everything at 10 gig. But so these are 80 channels, 80 optical channels, each running at 10 gigabit per second. And they're all on, right? So this is 800 gigabit, in this very, very small area. And the driver voltage, so measured, from the EIC on top of the PIC, the modulators are going at with 1 volt drive. Obviously you can have higher drive, but with 1 volt drive, we're getting 50 femtojoules per bit. This is with the entire chip, on. So this was, I think this is a record on the TX side as well, in terms of the energy consumption. And so, we made, the way we measure this, of course, is using bit error rates and so forth. And so you can see here that the blue curve is with 1 volt. You get slightly better performance if you drive the modulators with more voltage, but even with the minimal voltage with 1 volt, we get essentially error-free performance, down to 10 to the minus 12 and 50 femtojoules per bit. So that was really, really exciting for us to see. So then we also wanted to measure the receiver side. So this is just the TX side. And so we measured the receiver side. And the way we measure the receiver side is, the receiver on the chip has an error, essentially a bit error detector on it. And so we transmit bits and we count the errors. So it's essentially a bird that's on the chip electronically. And so this is the receive power down to 10 to the minus 10. This is really only because of the limitation of the actual electronics on the chip could only measure down to 10 to the minus 10 in the bit error rate, but this is essentially error-free. And so we measured physically, we measured just under 50 femtojoules per bit on the static power and about 20 femtojoules per bit on the this is on the receiver side. So just under 70 femtojoules per bit. So altogether, the TX RX interface is 120 femtojoules per bit. And this essentially because of the very, very good sensitivity of this receiver. And so this is kind of showing it all together. You can see the the package, and we have some control circuitry, and this is just showing so we actually tried to connect two of them together, and to get everything to work so we had completely separate modules talking to each other. Here's one MCM acting as the receiver, one as the transmitter, so really showing the data going. And when we sent it over 100 meters, we had to reduce the data rate per channel a little bit. There was a bit of a timing issue, so this is running at 8 gigabit per second per channel, for this 100-meter experiment. But still, very, very nice to kind of see that. All right, so kind of, just zooming out a little bit, what do we want to do with all of this, right? So this is a curve that I got from Fabrizio Petrini from Intel. Some of you might know him very well. Again, kind of showing how, the need for this I/O and memory bandwidth, and, how much this is going to continue to scale going forward. So zooming out again to the system level, the vision that we have is, to take these photonic chiplet I/Os that I just described, and be able to not just necessarily use them to take the bandwidth out of a socket that has GPUs and memory, but also to allow maybe the disaggregation of systems, so that to enable even a larger memory pool of high bandwidth memory, right? So let me just explain a little bit more what I mean. So, in today's sort of, confined architecture, I have the GPUs, and then I have the high bandwidth memories kind of typically around it. And then the I/O bandwidth that I get out of that socket is limited, as was mentioned earlier in the presentation. So yes, you can put, these optical chiplets that I just described, and now get more bandwidth out. And that would be great. But in addition to that, you could think about also just creating another socket with only high bandwidth memory on it, for example. And this would have the optical I/O capabilities. This is just one example. It could have like, terabytes of I/O bandwidth, going into just the disaggregated, or a socket that's just memory. And so we would not, we would have the best of both worlds, high bandwidth, but also more memory space as well, because we could just add more memory that's maybe a little bit outside, not necessarily has to all fit within that one interposer. And so that kind of, we can start to think about adding, transparent optical links, thinking about more disaggregated architecture. And that's another direction that we're thinking about these days. This would be also, creating a photonic switch fabric as well, kind of showing, how the numbers would work out. And then, lastly, we would like to think about, okay, what if we could have this optical connectivity, right? So you can imagine, we have a different, potentially the possibility of new architectures where we can communicate across the entire system. Yes, latency is always going to be still an issue, and so we have to mitigate for that. But what if you had the same bandwidth that you have within the socket available to you, system-wide? How would you map the applications differently? Maybe you can design things a little bit differently. We're not taking away electronics for sure, because but this is added capability on the system. So one just kind of something to have in mind, like let's say you have multiple jobs that you're trying to map onto a high performance system. Usually nobody really knows what the compiler really does, right? Or the scheduler really does. But, you try to map your workload, so that the nodes are close to each other, right? Especially the ones that have intense communication. But the optical connectivity, you can put the stuff kind of anywhere in the system. You'll still have the same bandwidth, again, with the latency consideration, having to be taken into account. And it just allows a lot more flexibility in terms of job placement and application placement. So just some ideas that we're hoping to consider in the future with this technology. And of course, I just want to thank, the students. It was a nice day in New York, and so we were outside, getting a chance to get some fresh air. So yeah, let me stop here and be happy to take questions and discussion.
Thank you, Keren, for a great presentation. So taking the occasion now, I would like to advertise the next vCast, which is going to happen in 2 weeks on the 13th of March. We will host Ashish Kapoor from Microsoft, who will be talking about deep learning for climate. So now we move to a Q&A session. Everyone feel free to either put your questions in the chat and I'll read them, or raise your hand and I will ask to unmute you. I can already see that Thorsten has a question, so feel free to unmute yourself.
Yeah, not only one actually, but I'll yield if somebody else has questions. So this is great. I mean, as you know, we are building these systems around it, basing on these technologies, and we have a limited understanding of these technologies. Always great to hear from you to gain more of an understanding. So when you build a system with this, you would probably require some form of forward error correction, I suppose. Or what are the error rates that we are talking about that are literally coming out of your device?
Yeah, good, very, very good point. So the goal here is to get to links that actually do not need the FEC, or at least very minimal FEC, because we're really trying to, especially for these applications, within the compute, trying to really minimize, these latency and added energy consumption. But so I showed some data, some errors that are sort of 10 to the minus 12, but really the goal is like 10 to the minus 15, 10 to the minus 18 on the errors. But yeah, I think that the technology is capable of getting there for sure. And but probably like in eventually in the systems will probably have some effect to it. But the requirements, let me just put it this way: fundamentally the photonic link can actually deliver a really, really clean link that can go very, very low in terms of the errors that you get.
I see. So you're saying 10 to the minus 18 is realistic from such.
Yeah, it's definitely realistic. Yes.
That's interesting. Does this also apply if I have some connectors? Because at the end I cannot build this as a single monolithic system, so I have to plug it together just for practical deployment purposes. What is happening there? Yeah.
So different. Right now it's a bit of a zoo. To be honest, so we're trying to get to, the community is trying to get to a more standardized ecosystem. So let me just clarify. There's kind of different applications, right? So if you just go to a data center that has optical, you'll see optical fibers there, and they're just pluggable, and those are InfiniBand or whatever they are. That's not what I'm talking about. That's different. This technology is going to live within the chiplet world, and so the concept is that you have some kind of a heterogeneous interposer that might have different kind of chiplets on it, and one of them would be the photonic IO chiplet. And so some of the there's a big push for getting, kind of a common protocol like CXL is the main one. And so, that would be the interface, kind of between, within the chiplet world. And in terms of, kind of the physical connections, right? Again, there's a whole different set of solutions, but at least so I'll give you my opinion here. There are some solutions that have fiber V grooves, and pigtails, and I think that's a non-starter in the world of computing. You just can't do that. So the solution is going to be, essentially, physical, optical I/O that just plugs, like a chip pluggable solution. And there's definitely a lot of work, that's being done. So basically the idea is to get the packaging as similar as possible to the way we do electronic packaging today. Yeah,
I understood that. That's interesting. Well, I mean, the problem with electronic packaging is, oh no, there's may not be a problem. Okay, so I have to think about it. That's a great point. If you don't have any other questions, I will just continue. I mean, I can probably go on. So what about the latency? So we are basically, your main assumption at the very beginning was that we are going broad, lower frequency for much better, all kinds of properties, like you get cleaner eye diagrams, you have less energy consumption, probably better signal, better signal at the sensors. What happens to the frequency here, latency? Sorry.
Yeah, so the inherent latency in terms of the electro-optic and optical electronic plane conversions is really tiny. There's like picoseconds or even sub-picoseconds. Yeah. So it's kind of a non-issue. So the latency is completely dominated by time of flight, over the links. So that let's say you're connecting, let's say you have some kind of a GPU rack sitting over here and memory rack over there. At least I'm taking out any kind of other software latency that comes in. I'm just talking about the optical link.
Yeah.
As soon as you get to the optical domain, it's just, time of flight, and it still could be too long if you're going over too much of a distance, for sure.
Absolutely. My problem is again from a systems design perspective. We just published a paper about issues at hyperscalers with Rocky, and one of the issues there is essentially FEC, because just collecting or any block-based transmission protocol, which we use in Ethernet today, for example.
Yes.
Because you just have to collect all the data before you can go over the parallel link. So you have to collect the word, and just collecting that word, as you go more broad, your word gets bigger, obviously. And you have some kind of input link, it takes a lot of time. So it can take like double-digit nanoseconds, which is a problem. I mean, this is already a problem. But you say you could probably change the system.
So this is a different interface, right? Yeah, so you're basically all the wavelength channels are essentially directly connected to the electronic, drivers. So there's no like SerDes and things like that at least in this design. So it's basically, you have whatever the parallel interface that you have on the electronic side. The idea here is that you directly drive those signals into the photonic link, and there isn't like I don't know what was the other design, but you don't have to spend any time like interleaving them or anything like that, because they're just all in parallel. And the same exact thing happens on the other side. It's just a completely parallel, interface.
Yes, I get it, but you're basically now telling us systems people change all your protocols to adhere to my to my interface, which makes sense. I mean, I think for this to be real, we the new technology people, the optics technology people, have to come to the whatever exists today, right? So whatever the electronic interface. Hopefully there's going to be some agreement that on like CXL or whatever that interface is, and we'll have to just meet that. But
from the technology side, there is no added like latency that you have to do the conversion to optics and back again or anything like that. And any significant latency.
Yeah, immediately following up on this, I have a question related to Ethernet. I mean, you could be thinking to use that technology in Ethernet, and I was at the beginning of your talk, I was actually wondering, as far as I understand, if I'm buying a 400G link today, this is going to be 4 times 100G, and the 100G is a single frequency essentially, as far as I understand. Correct me if I'm wrong.
That's correct. I mean, it depends on the module. Sometimes it's 25 gig, and then it's times 4, and then again times 4, something like that. It depends on, different companies have different technologies, but yeah, the number of channels that are actually used today, I think the maximum is 4, like 2 or 4. And so there's a lot of in the optical, there's kind of another axis in optical interconnects, that the ones that are commercially available, to just go very, very high speed per channel. So there's, going 800 gig per channel, but then, it's fine, if you don't really care about so much about, power consumption, or you don't care about, bandwidth density and things like that. And also necessarily you're going to have, as you go to these higher speeds, you have to have DSP, and you have to have the SerDes, in and out. Mm-hmm. And so all of those things, add power consumption and latency. But it's definitely a direction that commercial entities are going for sure.
But would you say that a commercial entity could basically take your comp laser and build an Ethernet link out of it, or am I missing something that would prohibit this in some way?
No, it's just exactly that. I mean, we could. It's just that the comb laser technology, all the stuff that I'm doing is still, I would say, kind of in the research domain, right? Yeah, so it's not. But this would be a replacement essentially for all of that. Yeah. But also, it's also a different application, right? There, no one is really thinking about doing those serial links, to the GPU. I mean, it's more like to the server, or to the, it's more like to the box or the server than directly, integrated, as a chiplet, within the socket.
Yeah, but that's the question, why? Because I don't see why. I don't see the difference between the GPU and the server, and we should really just connect. Like you said at the very end, we should really think about a system architecture that is kind of flat, and this technology may actually enable it, because with electrical we can't do it. With electrical, at the moment we go more than a centimeter, we have to put extremely heavy effects on it at very high bandwidths. Yeah, this seems to enable a completely different system design if you think about it.
Exactly. So, so I guess, just to kind of summarize, right? So there is like, let's call it the fat the fat link, which is not really fat, it just means highly parallel, right? Mm-hmm. With a lot of wavelength channels. That's sort of one approach, and then there's the other approach where they're using one or just a very small number of wavelength channels, really trying to increase the rate. So the technology, the optical technology for going on the narrow, very high speed per channel is very different. It's basically, you have to use these much larger devices, whether they're silicon photonic or lithium niobate, some other things, but they're basically these Mach-Zehnder modulators, and they have, heavy, RF drivers associated with them. And, they work very well for sort of connecting, just a physically larger thing, to a server or to a box, and going long distance with high speed. But it's not a technology that really works well when you're trying to kind of co-integrate on a chiplet. It's hard to put like a bunch of these RF Mach-Zehnders, for this application. So it's just, the technology sort of packaging and the match for the application that I was describing here, which is, within the socket. So for that, I think that it's going to be more of this parallel, because also energy consumption is very important. These 400 gigabit things, they're taking up a lot of energy per bit, because it's not the top priority for them. They're not inside the chip, and it's not maybe such a big factor. And it's easier in general if you have to only manage 2 or 4 wavelengths. It's easier than to manage 64. So our approach, definitely parallelism is has that complexity, but because of the comb laser, it does have some potential advantages, right? So like IR is maybe the closest commercial right now. It's not exactly commercial, but it's on the verge. And so they're using, I think they have like either 8 or 16 channels, so they're trying to go in this direction. They don't have a comb laser quite yet.
Nice. Thank you so much.
Yeah, sure. Yeah.